Good morning, everyone. So this is the third and last part, and today we'll talk about Pulse ENDOR. I just, in this mini course, what I did, I sort of squeezed whatever would be in an EPR course to 6 lectures, but of course this is subject to my own taste, right? So I put in the things that I think are important, the thing that I like, but you have to take it as that it has a subjective point to that. So not everything that I chose to show is really the most important things in EPR. They are just the things that I think are important and the thing that I like. So as you will see, Pulse ENDOR is a part that I particularly like, so this will be relatively detailed and relatively long with examples. So as we already, you've seen it a couple of times, we get structural information in EPR either by observing the hyperfine interaction, then we get short range interaction, or by electron spin-spin dipolar interaction, and this is what we saw yesterday with deer. So now we're focusing on this part, on the hyperfine coupling. And yesterday we went through continuous wave ENDOR that was mostly related to liquids, and now we go for solids. So so let's just look for an example. So this is a protein called azurin, and it has a metal site in it. It has copper. So now you see this on the left. You see this ball. So this is the copper. And because it's a transition metal ion, it coordinates to various ligands. So now we focus on this particular site. So you see the copper, and then you can see the ligands. So it has 2 nitrogens from histidines, and they are noted. So they are in blue. And then it has a oxygen from glycine, and it has a sulfur from cysteine. So often there is quite a bit of, so this site is known. Sometimes you have sites that are not known, and you want to know who are the ligands and how they are arranged, because this is usually closely related to the activity of the site. So this particular site, for instance, it's an electron transfer mediating site. Okay, so what can we learn from ENDOR? So here we focus on this, and now, so from the hyperfine coupling of the copper itself, we learn quite a bit on the electronic structure, so you can learn about the molecular orbital, which the electron participate, etc. And then this we saw that we can resolve in the EPR spectrum, right? But now we are really interested in the sulfur. In this particular case, it's very interesting because there's a lot of spin density on the sulfur, and because of this very covalent bond between the copper and the sulfur, this is a very good and unusual electron transfer site. So if we could put here sulfur 33, we could measure the hyperfine, and we could get some information directly on how much spin there is in the sulfur, and then relate it to the activity. Okay, and then we could also look at the nitrogen. So here we have these histidines, so they have these imidazole rings. So we have 2 nitrogens that are directly coordinated to the copper, and we have 2 that are further away. We can measure both in slightly different methods. So we want to see this N14. Maybe if N14 gets to be too complicated, we can maybe look at N15. And then we have these protons that are also informative. For instance, the proton up there on the cysteine would have very large couplings because it's near the sulfur. So this we can also measure. Now we can also measure deuterium if we do proton exchange. So let's see some other examples of hyperfine interactions that we want to measure that are just too small to be resolved in the EPR spectrum. So here is a nitrox spin label. And somebody asked me yesterday, can we measure hydrogen bond? So here is a water molecule, hydrogen bonded to this spin probe or spin label. And we know that from the EPR spectrum, we can get some ideas from the hyperfine coupling or from G, but it will not tell us really the geometry, where this bond is and the length of the bond, etc. So this can be done by ENDOR, and we will see it later. And here is another metal site in a protein, but this can, so here it's coordinated to a water molecule, it's a manganese, and to a histidine. And you can have the same thing in metal organic framework. You can have your paramagnetic metal coordinated to whatever. You can adsorb things and see how they are attached. Okay, so now when we work with the with ENDOR, these are the terms that we care about in the spin Hamiltonian. So although we have large hyperfine couplings to the copper, usually we can ignore them, and we look mostly at the important parts are the Larmor frequency of the nucleus. So this is the term that has Ni, and then we have the hyperfine coupling. So note that when we worked on the EPR, you can, or at least when it is isotropic, you keep only, it's enough to keep the secular term, the SZIZ. However, when you work with ENDOR and not at high fields, then you need to keep this second term that is called BSZIX. That is a non-secular term and mixes some of the states. So we can get structural information from A and B, and from the term of the nuclear Zeeman, we get the identity of the nucleus. Okay, so let's see what are these A and B terms. So A is given by the equation up there. So I took it as axial to make life easy. So it's A, so we see here on the left the axis system. We've seen it many times. So we are looking at the X, Y, Z are the principal axis of the G, and then we chose the magnetic field to be along, let's say, Z, and then we have a proton sitting somewhere with making an angle theta with Z. So this is our geometry. And now, so for A is given by either A parallel cosine square theta plus A perpendicular sine square theta, or we can break it into the part that is isotropic and anisotropic, and then we have the anisotropic part that's called T perpendicular, and down there on the left you can see how it's really very closely related to the distance, right? It's 1 over the distance cube, and this is for the case that we can use the point dipole approximation. So usually when we work with ligand hyperfine that are further away, like in this case, this would be okay. However, I showed you before in the imidazole, when you look at the let's say, so you have the nitrogen that is closely, that is directly coordinated, so then you cannot use the point dipole approximation because the distance of the bond is, let's say, maybe 1.8 or 2 angstroms, so then you cannot neglect the wave function. And also, the remote nitrogen, there was a nitrogen that was a bit far away. Also, this one cannot be used, cannot be described by the point dipole because it's a conjugated system. So the electron spin might migrate there. So you can, but it will not be correct, but gives you some idea. So now, when theta is equal 0, we measure A parallel. When it's 90, we measure A perpendicular. Now the B term depends on the same parameters, but it has a different orientation dependence. You see, it really depends on sine 2 theta. So again, the energy level diagrams, I think this you can already see in your dreams. We've seen it many times. So this is a spin half of an electron and a proton. And we have the EPR transitions, right? The green one are the allowed one, where the nucleus does not flip. And then you have the forbidden one, where the nucleus flip, but they are very weak, and currently we don't care about them. And then we have these two blue ones that are the NMR transition, and these are the ones that we want to measure, right, by endotech methods. So these are the nuclear frequencies, so they are given by this term. So you see that it has a dependence on A, and it has a dependence on B. Yeah, and the nuclear alarm of frequency is given by gamma B0. And if you change ms to plus minus half, you will get the two frequencies. Now, when you work at high field, then you can neglect this term, and then your lines are really very symmetric with respect to the alarm of frequency. However, if you are at low field and the B term becomes important, then they are not symmetric anymore. Okay? So let's remind you, so if we measure the EPR spectrum for this allowed transition, we see two peaks that are centered at G, and the separation is A. And now if we measure the NMR transitions, we get, for weak coupling, where the hyperfine is much smaller than the alarm of frequency, we get a doublet that is centered at the nuclear alarm of frequency and split by A. However, you can have cases that your coupling is bigger than the alarm of frequency, and in this case, the doublet will be centered at half the hyperfine coupling, and the splitting will be twice the alarm of frequency. So when you measure an ENDOR spectrum, what you do, you're looking either for splittings or for positions that correspond to alarm of frequency of something. So yeah, you measure the center, you go to the table, and you see which one it fits. If it doesn't, you try splittings and see which one it fits. Okay, so as we already mentioned before, we can do single crystal, but most often we're working with powders or frozen solution. So then you get a superposition of all possible orientations, and we can see here some simulations. So you see here it's a single crystal. So we have here you see two lines, and the splitting is A, and it's centered about the alarm of frequency. Now, if we have a powder and we have only A iso is equal to 0, so you see this very nice powder pattern, and A perpendicular is half of A parallel, and I think we've seen these already, these shapes quite often, and this is called like a bake powder pattern. Now in the one below, what we added, it's now you have also an isotropic hyperfine coupling. So what it does, it takes these two powder patterns, they look very much like the G powder patterns for axial symmetry. You take them and they move along. So now if you measure A parallel, A perpendicular, from here you can then derive A iso and T perpendicular. And now we go for the strong coupling case, and now you see, so when you work at high field, you are often, for protons, you are always on the weak coupling, and for nitrogens, it depends. So for a single center, like a single crystal, you see the splitting is 2 ni, and it's centered about A over 2. And now for the powder pattern, it's now a bit different. So you see, you recognize the perpendicular positions, right? You take, and they should be separated by twice the alarm of frequency, and the center will be A perpendicular over 2, and then you recognize the parallel singularities, and the center will be A parallel over 2, and the splitting will be 2 ni. So when you get this, you're trying to see whether, 2 ni should be the same for both regions. And in the bottom, we have another example that is just with different parameters. But you see this, often you have these nice line shapes that you can recognize the parallel and the perpendicular position. Often it is axially symmetric. When it is not, then of course it gets a bit more complicated. Okay, so if we work at conventional, if we do ENDOR at conventional X-band frequencies, then, you know, different nuclei would have large hyperfine, typically large hyperfines, and small and small Larmor frequency, like let's say N14 or 017. So it turns out that they all come one on top of the other. So it's really very difficult to assign. You see, if you have strongly coupled nitrogens and protons, they always overlap. It's very difficult to assign. Now you go to high field. So, you know, the Zeeman interaction of the nuclei gets bigger. So first the protons get out of the way. This is already something good. P31 gets out of the way as well. But you see downstairs, you know, down there, the 017 and 14 are still a bit one on top of the other. So this is at 95 gigahertz. So for ENDOR, it will be even nicer to go higher. Yeah, so if you go to 240, then you will separate all of them. So now just to show you an example, so this is a copper histidine complex. And so we have the copper is coordinated directly to the N14. And these have large couplings. So you see they sit right on top of each other. So this blob here that we see on top is a superposition of N14 and proton. Protons, there are some tricks to separate them, but you know, you can guess that the shoulder at the end is maybe protons, and you look for some symmetry along the Larmor frequency. Here, and the bottom one, and here the scale was plotted as the RF frequency minus the proton Larmor frequency. And then you see it's really nice. We see the protons, the nitrogen are somewhere very far away. And you can identify, you see you have these two shoulders at the end with a coupling of about 11 megahertz. And then you see all these different singularities. Now, it's still not easy because you don't know if these singularities that you see, are they the A parallel of a certain proton or maybe A perpendicular of another proton. So you have to go through some effort to analyze this. Now, when we work at high field, you also have first order expression, so it's very symmetric through the Larmor frequency. So if you have a line here, you should look for the line on the other side, right? So this is also some guidelines. Okay, so now we talked last time about CW ENDOR, and what we will do today is about pulse ENDOR. So what are the advantages of pulse ENDOR? With pulse ENDOR, you can, just like pulse EPR, you can start playing with the pulses. You can manipulate your spins. You can, use different sequences. So there's a lot of place to maybe resolve spectra or to go to 2D and etc. And also, it is not so sensitive to all these. You remember we talked about we had to have the right relaxation pathway not to get bottlenecks, so you don't have to worry about looking at the temperature that will fit. You know that if you go to low temperature, the lowest, the better, and that's it. Now, the line shapes that you get are usually more accurate, and they don't have artifacts. And this I said. Now, there are, of course, disadvantages, and it's very difficult to apply to liquids. So you really have to have very special cases where it works because of the limits of the relaxation time. And then you have to measure it, so you cannot. And then you have to do it also at low temperatures. But see, for radicals, you don't have to go very low. For metals, you have to go lower. So let's introduce the first sequence, and the first sequence is called Davies ENDOR, and you see, it's really old, from 1974. And now, on the right, we have our EPR spectrum, right? We have a doublet, so we forget now powder pattern, and we have two lines. And now we come with the pi pulse. You see, with the microwave, with the pi pulse, and we invert this particular line, then, so we are watching this line all the time, then we come with an RF pulse, that is a pi pulse, and then we detect. Okay, so now let's see what happens. But what it is very important that we hit only one of these lines. We have to be selective. So you already used to see these 4-level systems. So now we have the 2 green ones at the bottom are for the electron beta state, and each one corresponds to a different proton state. And the upper ones are for the electron alpha state, and the bottom one are thick because they are representing more population than the top one. So now we come with a microwave pulse that is selective, and we give a 180-degree pulse. So what it does, it inverts this particular transition, right? So now if it inverts this particular transition, and I would not do anything, just do an echo detection, I will see a negative echo, right? Because it's in emission, right? I have the upper one. Now I come with the RF pulse, and I'm hitting now the upper NMR transition. Yeah, so it's, if you look in the middle, yeah, the upper one, and I transfer the population, I transfer the green to the other manifold. So now what happens to the line that I observe? There's no population difference, it disappeared, right? Okay, so now you see the line that I was inverting, I have no signal. Yeah, so it went from -1 to 0. So if I go from -1 to 0, I see a peak, right? So now I scan. Okay, so this shows you what happened when the RF did not match with either the NMR of Ni alpha and Ni beta. And now I go on the other transition. So now with the RF, I'm inverting the bottom one. Yeah, so again, for the transition that I'm observing, I equalize the population. And again, the signal went from -1 to 0. So now if I just scan my RF and I look at the echo intensity, I see this nice doublet that I measure. Okay? So now, of course, I don't know who's alpha, who's beta. So I see a doublet, and the center is at Ni I, and this is the difference. Okay, so this is the Davies ENDOR experiment. Now, you can see that if I get the hyperfine coupling is small and small and small, then it's very difficult for me to do this inversion. So this method is better for larger couplings. If you have a coupling of 1 or 2 megahertz, you should use another method that we will talk about it later. Okay, so the echo intensity is given down by this equation, and you can see that if, and beta is the flip angle of the RF pulse, so you see that if you put 180, your echo goes to 0. Now you can imagine that this is never the case. It's never going from -1 to 0. It goes from -1 to -0.98 or 97. But you always see this effect. This is just for the explanation. Now the ENDOR efficiency is given by the difference between the echo intensity with the RF on and the RF off minus RF on divided by RF off. And usually it's between 1 and 0. And depending on the system, if you have a powder pattern and broad lines, your RF anyway touches only a few, so it's usually a few percent. So the sensitivity of ENDOR is much less than the sensitivity of EPR because the signal is, let's say, 5%, so it's almost an order or 2 orders of magnitude less. And this is in general. Any fancy experiment that you do, immediately you lose quite a bit of sensitivity. So measuring EPR is really very high sensitivity. The minute you go to this type of experiment, DEER, this, you go down considerably in sensitivity. As I said, if the pulses are not selective, we don't see the ENDOR effect. So this is called the hyperfine contrast selectivity. So sometimes you want to disentangle your spectrum because it's too complicated. So you can measure it twice, once with a short inversion pulse and once with a long one, and then you kill some of the small couplings and you're left with a large coupling. So here you see, for instance, on the left, you see this hole as a function of the first inversion pulse. So if I give an inversion pulse of 400 nanoseconds, you see my hole is very small, and anything outside this hole, I will have nice ENDOR. Now I go to 100 nanoseconds, so you see this hole is broadened, so there are many more hyperfine couplings that I will not see. And if I go to 25 nanoseconds, you see if I have a coupling of about 2 megahertz that is determined by this red arrow, you see that these lines will be tiny. But if I have a large coupling of about, 15 megahertz, then this will be already larger. And this is just an equation here that you can use that gives you the selectivity parameter that gives you the ENDOR intensity relative to the width of the microwave inversion pulse and the hyperfine coupling that you want to see. Okay, so now let's just see an example. So this is this is concanavalin A. It's a manganese-containing protein. You can crystallize it. It has been also solved for the crystal structure is very, very high resolution. And the question here, so you see the manganese is coordinated to a histidine and then to two carboxylates, and it has several water. Now, a crystal structure usually cannot give you the positions of the proton, and the idea here was, can we do proton crystallography? Can we do by ENDOR determine the positions of these protons of the water, or of the position of the proton of the histidines? If you know the structure of the imidazole, you know already where they are, but in water you don't know. So this was the idea of this work, and it was done on a single crystal. So here is a single crystal of this particular protein. You can get it to be pretty large, and then you have to put it in here. So here you see the W-band tubes. This is a size of an Israeli coin, but it's like, I think, a penny, an American dime. Everybody knows the American dime? I don't know the Australian, but it's small, okay? So now, then you see here, you see, so at the bottom you see the tubes, and one is, so they are just filled with solution of metalloproteins that have color, and so you can see. Then you have above it, you have the cavity, and you have, so this is a cylindrical cavity for W-band, and it has slits, and the RF coils come above and below. And then you have this on the right. You see that's where you insert your sample, and that's where it goes into the cavity. And this is the size of the waveguide. I told you that you have to connect all these waveguides. So if anybody saw an X-band waveguide, it's this big, and these are very small. So here's a little bit of instrumentation. Okay, so now you put this single crystal of concanavalin A into the X-band, and you do a rotation pattern, and it really looks pretty bad, right? It looks almost like a powder pattern. Now, if you do it at W-band, you see the central transition is very narrow, and now now the broad, you remember it's from all the other transition, there's a distribution of D, so it's not really very well resolved. But if you look at the center 6 line, they are very resolved, and you see that as you change the angle, you see that once you see one set, then you see two sets, and this is because you have two manganese per unit cell. Yeah, so you have two that have different transitions. Okay, so now we want to do ENDOR on a high spin system. So it's getting a little bit more complicated, but not too much. So you remember we have all these transitions of the manganese, and now it's coupled to a proton. So now we forget about the manganese coupling. It's big. It doesn't affect the ENDOR frequencies of the proton, so we ignore it. And we split each one by 2, yeah, because of the proton. So on the left, we have the M sub S. On the right, we have M sub I. And then, so now when we excite from 5/2 to 3/2, then we will see the ENDOR frequencies that correspond to these two levels. And if we excite the minus 3/2 to minus half, we will see the two sub-levels that correspond to this. I will show this in a minute. So in general, in this case, the ENDOR frequencies to first order depends on Ni minus MSA. So you see when MS is large, you get larger ENDOR frequency. So if you add them all together, you get this 6 ENDOR lines, right? Because we have 6 manifolds, and it's symmetric relative to the nuclear Zeeman. Okay, so now the ENDOR, if we can selectively look only at this transition, then one below will give us the line corresponding to the two ENDOR frequencies that we see here in the bottom. And now if you plug it into this equation, you see that these are the two most, the highest frequency lines. Yeah? And now if we go to the next one, we see they move in, and then for the half minus half, they look like a spin half. It's symmetric about the Larmor frequency, and then they go to the other side and to the other side, and if you add them all, you get this type of a pattern, and you see that the outer ones are a bit weaker, half the intensity than this. Okay, so this is what you expect to see for this concanavalin A. So now we know that the half minus half transition is very sharp, so it will dominate. But under this, yeah, you have some other transition, and you can see the others, but much weaker. Okay, so usually we see mostly this one. So here is the site now. Yeah, so now you see the manganese has 2 water molecules, and it has this imidazole, this histidine. So in principle, we should see the 4 green protons that are water, and we should see these purple ones that are of the imidazole. And then, of course, when you do a rotation pattern, you see each one, and it's a bit complicated. So first, how do we tell which is which? So this can be very easily done. So here, the blue spectrum is recorded. It's a particular orientation. So you sit on one of these, so you see the spectrum has 2 components. You sit on one, so you select mainly one site, and then you record your ENDOR spectrum, and you see all these lines. Now you go and you prepare your crystal again, but you prepare it in D2O, so the water signal disappear, and then you know which are your imidazole lines and which are your proton lines. Okay? Then you have to be very patient, and you put your crystal in the spectrometer, you record a certain orientation, you record your EPR spectrum, you find one line, you keep following always the same line, and then you do your ENDOR measurements in the 2 different sites. Yeah, and it doesn't matter if you take one line or the other, it's the same. And then you rotate it a bit. and you do it again, and you rotate it a bit, and you do it again, and in the meantime you pray that the spectrometer doesn't break and the helium is still there, but eventually, you know, you can do it. So then you have to sit, and to analyze everything. So here I show it to you already after it has been separated into different protons, and you get these rotation patterns for proton water 1, proton water 2, 3, and 4, and you get the same thing for the imidazole. For the imidazole, it's good just to test, because then you compare with the crystallography that you get the right position. And you see from this, you can extract the hyperfine and isotropic part, the anisotropic part, and the angles with respect to the crystal orientation. And each one has a different one, and you see it fits pretty well. And just to show you that this, in principle, you can make these type of measurements. And then after this, you can place your proton on the crystal structure, and then you can see that they are involved in certain hydrogen bonds, and this is some type of information that you get. So this was the single crystal, and now we go to powders. Okay, so when we go for powders, you remember we talked yesterday about orientation selection. So now if we take this, let's say, azurine, so frozen solution, we will have this very broad pattern that we've seen before. Again, we have the same structure here, but now you see that the proton is not coinciding with the direction of the bond to the proton does not coincide with the direction of G parallel or perpendicular. So when I select, for instance, this position, I'm selecting the orientation of the field relative to the copper that is 0 degree. But the proton will not be 0, will be something else that is dependent on the structure, right? So it depends on the relative position of the proton to the axis of the symmetry of the copper complex, okay? So if I record the spectrum here or in the middle or in the side, I will get different spectrum. So here, for instance, as example, so if I'm placing my field along G perpendicular, I will select this particular molecule because the black part corresponds to G parallel, and if I want to, and if I will put my field along the G parallel position, then I will select this. So you see, only very few really contribute to my signal. So it's like a poor man single crystal, right? When we did a single crystal, it was always a single orientation. But now there are places in the spectrum that it's single crystal, some is more, but I still have orientational information. So this type of measurements really give you the information between the relative orientations of the G and the hyperfine, which is, it gives you the orientation of where your nucleus is, So you have to collect this series of measurements. So let's see an example now. So now we have an example where the A and the G coincide. Okay, so now if I put my field along here, along G parallel, then I will also measure A parallel. So this is a simulation which gives us the ENDOR spectrum as a function of position within the spectrum, and this is these are the parameters of this proton. So it has a perpendicular of 8 megahertz and a parallel of 12 megahertz. So when I put my field on the G perpendicular, now if I put my field here, I will measure the 8. And in between, so this set of orientation selection, when you have coinciding tensor, we always have narrow lines. Okay, so this is an easy one. Now I have another case in which there are 90 degrees one with respect to the other. Yeah, so I have my A perpendicular is along G parallel, okay? So now what happens? So now I record the spectrum as a function within this powder pattern going from G parallel to G perpendicular. So now you can also imagine that when I work on the G parallel, my EPR signal is this small and my SNR is bad. But in the simulations, everything works. So now if I measure here, this is the, so now I see the 8, the coupling of the 8, right? Because this is, I see the A perpendicular. But now what happens when I put it here? So here, you know, it's the whole plane, right? Because it's axial symmetry. So when I put it along G perpendicular, I see the whole plane. So then I see from 8 to 12. You see, I see a powder pattern, right? So just by doing these measurements, I can immediately tell if I see a powder pattern along G perpendicular, I know that the axes are not coinciding, and you can do these experiments and really find the angles. And we'll see an example in a minute. So now, if we have copper, now when we do this orientation selection, it's a bit more difficult because we have both the hyperfine of the copper and the G that contributes. So it's not such a simple picture, but you can do this. So you can, with easy spin, you can record each. So you see each of these lines in the bottom correspond to a different MI state of the copper. So, and then if you add them all up, if you take the projection, you get this powder pattern. Right? So now suppose I sit here. Yeah. So when I choose here to do my ENDOR, I will get the following angles, right? So from one manifold, I will get around 20 degrees, you know, the range around 20, and from the red manifold, I'll get around 60, and from the other two, I'll get from 80. So I'm not really very selective. I have quite a bit of orientations. If I will go to the end, of course, I will be selective. Now I go to W band. So you see, now I'm very selective. Right? This is the same thing for W band. So now when I sit on, because now they are determined mostly by G, if I sit in the G perpendicular, it's very selective. So if you want to get really orientation selection very good, you go to high field. Now this is just another example of a powder, and this is manganese with ATP. We see again only the half minus half. And here you see the phosphorus line, so you immediately, this is the Larmor frequency of phosphorus, this is again W band, and you see that there's some difference between these two complexes. And you get this hyperfine coupling that is typical for this. So here we don't have orientation selection because we have this manganese, and the half minus half is very narrow, so there's no orientation selection, and all the orientations contribute here. And you see the anisotropy is not very large. Relatively, it's about 2 megahertz, which is the width of these lines. Often, as I said, it's easier to, instead of looking at the RF frequency, to look at the RF frequency minus the Larmor frequency of phosphorus. So then I can really read immediately from the position of the line, I read the hyperfine coupling. Yeah, so it goes from 2 to minus 2, so it's about... it's about 4.5. Okay, so now I'll complicate it a bit more. And now we have aqueous manganese. So this is a very simple sample. So this is what we saw before for the single crystal. And now if we have this powder pattern here, and we measure in position A, we get this powder pattern. You see a nice powder pattern that is pointing to here. Yeah, you see this arrow. And you see this is this Pake tablet, and at the middle you have some contribution from far away protons, but you see this nice Pake pattern from the water, and you can immediately read from here what is the coupling of the water. So this is usually very easy. If you want to know if manganese has a water ligand, this goes very easy. Now you see that the arrow, yellow arrow points to a point that, see, it's not very symmetric, and I was telling you that it should be symmetric. So there's an extra intensity here, and the extra intensity comes from contribution of other transitions. So now we can move the place where we do the ENDOR, and we move it to position B. So when we move it to position B, we see mostly this transition. And now, you remember this one is not really, so here I see the line corresponding to the -3/2 and the line corresponding to the +1/2. So you see, I see half of this Pake pattern. You see -1/2 perpendicular, -1/2 parallel. This is half of the Pake pattern that we see below. And then we see a Pake pattern due to the -3/2. And you see that it is broader and it has the right ratio. Okay, and from this actually you can really get the sign of the zero field splitting. You have to move on. Okay, so now there is second very popular sequence called Mims ENDOR. It's even older, from 1965. So now here you give your stimulated echo. So now you see why you were asking why you care about stimulated echoes. So instead of your first pi pulse, you give your inversion as a pi pulse, you wait some time tau, and then pi over 2, you wait some time tau, and then another pi over 2. Then you stick it your RF. So now if you don't have an RF, you have this echo intensity. Once you stick in the RF, the echo intensity will decrease. So when you do Mims ENDOR, you look at the echo intensity as a function of the RF, and this time it will not be positive, but it will be negative. Because in the Davies we had a negative echo that became smaller. Now we have a positive echo that is becoming smaller. So usually you see it as negative lines, and sometimes people just invert it so it's easier to see. So this is just a single crystal of copper 2-doped L-histidine, and you see many proton lines, sharp lines. Of course, it's a single crystal. And for this sequence, you don't have to be selective. So you can give you can give short pulses. So in principle, it's more sensitive. Because if I give short pulses, I excite more spins for my whole envelope. But you gain somewhere, you always lose somewhere else. So you see the ENDOR effect. So this is, or the echo, the ENDOR effect is given by for beta of 90 degrees. So the angle of the RF should be 180. Sorry, this is like before. But then the ENDOR effect is dependent on 1 minus cosine the hyperfine coupling time tau. So this first period tau goes in. So the ENDOR effect is modulated with the hyperfine coupling, which means that you get blind spots. So when, let's say, A times tau is equal to 1, let's say 1 to 360, right? So you get here 1. Then you have no ENDOR effect. Okay? So just let's see that this really happens. So this is another single crystal, and now you measure it as a different, so these are proton lines, and you measure it as a different tau values, and you see every time you get a different line. So if, for instance, you have a very broad line, and you see, so if you make your tau, so usually when you work with this Mims, you have an idea what your splitting will be, and usually you want to work for smaller couplings. So usually Davies is for large couplings, Mims for smaller, and then you want to put your tau as small as possible such that these blind spots will be outside your spectrum. Now you cannot make it very, very short because you have your dead time. So here it's just a ENDOR of coal done at Cuban. This is proton, so there's just very broad line of many different protons. And you see when you do it with a tau of 100, you see some line shape. When you do it with 1,000, you see all these blind spots. Yeah, so this is this modulation of A tau. So just now compare these two sequences. So Mims is better for small couplings where the blind spots are not a problem. For instance, if you do deuterium ENDOR, the couplings are usually small because gamma is small. You always do Mims ENDOR because it will be difficult for you to be selective. When you have larger ones, you use Davies. Now, in Davies, you don't have blind spot. You just have this blind spot in the center. But the Mims is more sensitive. So sometimes when you have lousy SNR, you go for Mims. So here is an example. So this is exactly the question that I was asked. So this is orientation selective Mims ENDOR at 95 gigahertz. So you have here, you see you have this particular copper complex. And now the question was something about the structure. So a deuterium was put up in these two rings. And the question, and the orientation of this ligand with respect to the G parallel was of interest. So then what you do, you go and you measure your deuterium ENDOR in different places along the powder pattern. So you know we have this powder pattern, and you see how the spectrum changes. I think the red is the experimental spectrum. So you see the coupling is tiny, right? You see the coupling goes from 0.5 megahertz to maybe 1.5 megahertz. And the reason it was not protons because there was interest only in these. So you do a selective labeling in this position, and then you can simulate it. You have to take into account also the quadrupole coupling of the deuterium. We'll talk about this later, but you see the fit is pretty good. You fit all of them, and you see a distance of 3.12, and this is the angle and the isotropic coupling. Yeah, so now you got all the information that you wanted. This is the angle relative to G parallel. If you know where G parallel is, then you get the geometry. If you don't know, you have to determine it. So sometimes people don't know the direction of D, but they know the structure. So they use the structure to determine the orientation of G. Here is this another example that somebody asked me yesterday. You can determine the orientation of hydrogen bonds to nitroxides. And this was done again at W band. And you see they determined here the orientation of the, so they put deuterium, and they determined the hyperfine, the quadrupole, and the relative orientation. They measured a different position in the nitroxide spectrum. They did it in several solvents, and they did this fit. So I don't want to go into all these details, but this is something that one can do. We talked about the protons, and we saw phosphorus, and I talked about deuterium, but I rushed through. So let's go back. What happens if you have coupling from a nitrogen or coupling from deuterium, that they have a spin 1? So in this case, we have, so the first order equation is given up there. So you see you have the, and I apologize, throughout these lectures, the Larmor frequency is sometimes noted as Ni-N and sometimes as Ni-I. But I think you can bear with me. So you see, if we didn't have the quadrupolar splitting, then you recognize the two terms are the terms that we are used to, first order. And then when you have a quadrupolar interaction, you have further splitting for n equal 1. For I equal 1, it's given by this term. And P is, again, is orientation dependent, so it depends on the orientation of the quadrupole tensor relative to the within the molecule. And if we take that A and P coincide, and we take angle theta equals 0, so then P here is equal to PZZ. And now we have the following. So we have 3 levels in the bottom. Yeah, so the beta splits into 3, minus 1, 0, 1, the upper to minus 1, 0, 1. And then we have 2 single quantum transition for each. And then we have the gray one that is a double quantum transition. The double quantum transition is at high fields usually forbidden. We will see later that it's not so forbidden in other experiments, but for ENDOR usually it is. And then what we see these 2 blue lines. So now the spectrum will be centered about the Larmor frequency. If it is the weak coupling case, if it is the strong coupling case, it's a bit more complicated. So it's centered about the Larmor frequency, and then we have these 2 doublets. The center of the doublet will give us the distance between the 2 centers of the doublets will give us the hyperfine, and the splitting within each doublet will give us the quadrupolar coupling. Okay, so each spectrum of the deuterium that we had before had this quadrupolar splitting. Now this quadrupole gives you also a powder, so it's a bit complicated. Okay, so this is what you expect to see for nitrogen or deuterium. For nitrogen, it will be the quadrupole is much bigger than for deuterium. And this is for axial symmetry. You remember when we talked about the Mims ENDOR, we said that it is tau dependent. The ENDOR effect is tau dependent, right? And it's modulated with A. So those who are NMR spectroscopy say, okay, so just do a 2D experiment, Fourier transform, and find A. So you can do that. So here, this is the famous DOTA, gadolinium coordinated to this chelate. And this is a chelate that we use quite a bit for distance measurements. And one of the claims that we say that it's good is that the spin density is only on the gadolinium. So when we think about distances, we don't have to worry about spin going all over the place. And this is because it's an F ion, and this is some of the properties of the F ion. But we thought that maybe we should measure it and see that this is indeed the case. Okay, so here this Mims ENDOR was done, and the idea was to look at the nitrogen and see whether what's the hyperfine coupling of these nitrogens. And this was measured at, so the Larmor frequency of nitrogen is 10 megahertz, so it's really not a very easy measurement to do, but Alberto did very nice, and he got now this powder pattern. But you know, and he measured it at several taus, and when you look, you don't really know. Is it the quadrupole? Is it the hyperfine? What you see this nice powder pattern, and what are these little things in the middle? So he did a 2D Mims. So here on the axis below, yeah, on the horizontal axis, this is the RF frequency minus the Larmor frequency of the nitrogen. And on the right, on the perpendicular one, he just measured it as a function of tau and Fourier transformed. So now you see that on the perpendicular axis, it gives you the hyperfine coupling. And you see hyperfine coupling is very small, is 0, and most is 0.6, and the quadrupole is large. And these little lines in the middle, they come from contribution from other transitions. It's part of the signal from the other transitions. Then he could simulate it very nicely using this hyperfine and the quadrupole of the nitrogen. So you can do this type of experiments. Now, I just want to show you that when you do ENDOR experiments, your line shape often will depend on the type of experiment that you do, and you have to worry about it. So this is just a spectra of manganese bicarbonate. Again, we see mostly the half minus half. And this, the first spectrum, so it's a C13 bicarbonate. So you expect to see coupling with C13. So this is a Mims ENDOR done at a particular tau that is supposed to be small enough. The coupling, you see the coupling is about 3 megahertz. And this is the line shape that one gets. And because it was sodium bicarbonate, you see also a signal of the sodium. Yeah, so you have the manganese coordinate to the bicarbonate, and somewhere there's sodium, and you see the sodium. So now this is the Mims. Now you do an ENDOR, a Davies ENDOR. And here you see it's very long pulses, but still you killed quite a bit from the middle, right? And now if you take, you can also do what is called FID detected Davies. So instead of detecting with an echo, you can put a very, very long pulse that burns a very narrow line, and you can detect this. So this one usually would have the least distortion, and you can see the last one has a different line shape, which is probably the correct line shape. So what happened in the first one, you had some blind spot distortion on the sides. Here you had some blind spot distortion in the center, and this is probably the nice, correct powder pattern. Okay, so now how do we determine the RF pulse? So here you just do a nutation experiment. So if you want to determine it, so what you do, you just run a dirty, what you call ENDOR. So this we use lithium fluoride. And so if you look at the lithium line, this is good for nuclei around 50 megahertz Larmor frequency, and the F19 will be good for protons. And now what you do, so you run this particular spectrum, and then you choose a particular line, you fix your RF, and then you look at the echo as a function of the RF frequency, the RF length. Yeah? So then you see, this is on the left, you see for the lithium, so you see it oscillates. If you Fourier transform, you get your what you call your omega 2, and from this you can see what should be your pi pulse, right? So for this one, you can put it, I think, maybe 20. And now, if you do it for the lines of the fluorine, then of course the fluorine has a higher gamma, so you get faster oscillation, and your pi pulse would be shorter, and then you can determine from here your the position of your pi pulse, and then when you come with your samples, you use this. Usually your sample does not have such strong ENDOR effect that you can, to get it on a protein will take you forever. So this gives you a good measure. So if you want to, you can do this. So it's the same. You can do it for the Davies the same way. You sit on one of the ENDOR lines, and then you increase your RF pulse in steps, and you get these oscillations. Now, there is another thing that we have to worry about, because if your RF is too short, it causes broadening. So often, for proton, if you work with proton single crystal, like the work that was shown you before, the single crystal of the protein had very narrow line. Now, if your RF is very short, then it has a certain width. So now so this shows you the ENDOR, how the echo intensity looks like when you come with your RF. So if you have an RF of 2 microseconds that is too short, you see your ENDOR line will be broad, and as you go to lower and lower, to higher and higher pulses, it becomes narrower. So let's just see how it works. So this is our this is our endo line, and now we come with our pulse. So the pulse has a certain width, right? And the shorter it is, it has a larger width. So you see, when we come here, it doesn't touch any of the signal, the endo signal, so we get 0. But now when it is here, you see, although it is outside the signal, part of it already overlaps. So then I broaden my signal. Yeah? So you see, although the center frequency does not touch it somewhere, the bandwidth, it does touch it. So this is called broadening, and you have to worry when you have broad signals, it doesn't matter. How can we improve if we want to improve the sensitivity? So it's possible, instead of giving 1 RF pulse, let's try to give 2. So how does it go? And this was designed, this is called special triple, and this was designed initially for X-band. So, yeah, so we give 1 pi pulse, and then we give another pi pulse, and 1 is given on the alpha frequency, and 1 is given on the beta frequency. So you go here and you invert your population. So first you have your inversion pulse. You inverted your population. Then you come with the RF on the alpha manifold, and you get to a situation that you go from a signal that was plus 1, you go then to -1, and then from -1, you go to 0. Yeah, so the difference is 1. Now, before you detect, you can say, okay, now I can go on the beta manifold and give the RF. Now, if I work at a high field, in protons, for instance, I know they are symmetric. When I'm at low field, it will not work because they are not symmetric because of this B term. So what I can do, I can just, I start from the center, and 1 RF goes this way, and the other one goes this way. So if one hits one line, the other one will hit the other. And when I do this, now I go from a difference of -1 to +1. So my ENDOR effect will be just twice. But then I have only 1 line. So I usually like to see the 2 lines, because if signal to noise is not so good, if I see it on the other side, I'm happy. You have some people that take the spectrum, and to improve line, they mirror and add them. I don't like this. So as though this looks very nice, whenever you add another pulse, there's some T1 taking place there, so you may gain on something and lose on something else. So it's not always working, but you can play these tricks, and here is just a nice example. So you see the black, it's a single crystal of copper histidine, so when you have these nice single crystals, everything works. And you see here the black shows you the proton ENDOR of the normal Davies ENDOR, and this in red is with this trick of 2 pulses, and you see it really increased a lot, and then it takes half time to record. If you want to do it at X-band, where it's not symmetric, then you have to introduce a pi pulse in the center. So when you introduce a pi pulse in the center, you invert the alpha and the beta, and then you are staying on the same transition. Yeah, so what happens here? So as you know, we give the first inversion, then we go on the alpha. Yeah, but now we need to invert them so we can go on the alpha again. And then if we do that, we get to the same difference in population. But then you have to put another pi pulse in the middle. It's more complicated. It's another reason to go to high field. Okay. So you see, with pulse ENDOR, you can do lots of games. Now you can do hyperfine selective ENDOR. So normally in the Davies ENDOR, we have the microwave, so we have one microwave frequency, so we give the inversion and we give the detection on the same frequency. And then we have the RF. Now you can do some sort of a triple experiment. You can invert with one, and then you can detect with another. And you have your RF. So let's see what happens. So I invert the first transition, So this is the usual one. And I detect, and then I transfer the population. And if I hit the NMR transition, I should reduce the intensity also of the other line. So in this case, I will get an ENDOR effect only when the difference between these two microwave frequencies are the hyperfine frequency. So sometimes when I have a very crowded ENDOR spectrum that I don't know who's who, I can try to do this experiment and see which are the lines that belong together. You can also do it as a 2D. So this is another experiment that one can do. So you can now do an experiment. Instead of having two microwaves, you can have one microwave and two RFs. Okay? So this experiment is called general triple. And what it gives you relative signs of hyperfine, and also it allows you to resolve lines. So let's see how it works. So here we look at, again, so now we have to have two protons. So if we have two protons, we have eight levels, 4 and 4. So the bottom one will be the beta of the electron. The upper will be the alpha, and then all the possible nuclear states that they give us 4. Okay, so now we inverted 1. Yes, we inverted 1, and we applied with the RF2 on one of these NMR transitions. So we have no signal. Now we come with the other line, with the other RF. So if we go back and RF1 equal to RF2, then we get back again a negative echo. However, if the RF1 corresponds to a line in the other manifold, then I will get a strong echo, right? Because I move population, so the difference now will be in the bottom will be large, and then in the top, and then I see an echo, right? So now if I do this type of experiment, so if I do the triple, so now I inverted, I touched one of the transitions, I will see all the transitions in the other manifold will show up as positive. So now I can take the ENDOR and the triple and subtract, and I see where the two peaks are. If they are on the same side, I know that they are of the same sign. If they are on different one, they are different signs. So see here, this is how. So if we have two protons, we have a doublet of doublets. Yeah, we have two doublets, and in red I show the alpha, and in blue the beta. So if they are opposite sign, they will appear in different sides of the LAMO frequency, and if they are in the same, they appear like this. So by doing this experiment, I can tell, and sometimes it's important for electronic structure. People like to know the sign of A, and this is just an example, and you can also use it for assignment. So here is a spectrum of irradiated malonic acid. Let's look at the top. So at the top, we see that we have 3 hyperfine couplings, the big one, A1, A2, and A3. Now, I think the big one is already in strong coupling case. And now we come and we do the triple. So we sit on the first line, on the first line, and we see that when we sit on the first line, we see from only one line from the other doublets, and this is the one from the opposite manifolds, and you see they are negative. So you see that they have different signs because one comes from on the same side and one is from the other side. And then we can do the same thing on irradiate another line, and we can see which come up and which come down. In principle, you can do this as 2D, and you get quite a bit of information, but this would take very long time. So another way that we can measure the hyperfine coupling is called by variable mixing time ENDOR. So now you do your experiment, the usual ENDOR experiment, the Davies ENDOR, but now you add a mixing time. So usually what you want to do, you want to put your detection as close to the RF. Now you don't do that, you put a long time there. And now let's see what happens. So we're working at low temperature, so this we've seen many times. So so this is what happens with the pi pulse. If we don't have any RF, we wait long time here. So the electron will just relax, and we measure a positive echo, right? Nothing happens, so we invert, and it goes back. Now we did the ENDOR. So we moved it to, so we moved it to the other manifold. And now we look here, we have a zero signal. So relaxation takes place, but it is on this manifold, and T1n is usually long. So we stick all the population on this end. Now, if we do now on the beta transition, right, then all the population gets stuck not on the right, but on the left. Okay, so we did it with the beta. We moved to here, it relaxed, and it doesn't go back to equilibrium because the cross relaxation and the nuclear relaxation are slow. The close, it can also go back from equilibrium from the top to on the diagonal. This is called cross relaxation, but if these two are long, so then what we measure, so this is the black box shows when it's not on, the RF is not on resonance, and this is when it is. So you see that if you do that, you get one line up and one line down, and usually you know which one should be up and which one should be down, and then you can get their sign. So just to show you an example, so here again with single crystal of doped copper histidine, so this is the spectrum, and now we start increasing this mixing time. So you see some line disappears, some stays, right? So you see this one is here, the other one is gone. Now, this one is here, the other one is gone. So you see that they have opposite signs. You can get the absolute sign. So we could tell each one which is alpha and which is beta. So this works also for powders, and this is for copper histidine in D2O. This is so we see here the large coupling that you see is from the alpha proton. It gives like 10 megahertz, is relatively isotropic. So you see when you put a short mixing time, you have, it's symmetric. When you put a long one goes up, one goes down, and you get the sign of the couplings. So this is all these things that you can have fun with the pulses that you cannot do so much with CW. And I think with this, we're done.